Uh, may I start presenting the lecture, Hayden?
Yes, go ahead.
Okay, so our next lecture is on chemotaxis. So after we learned how to apply forces on cells, we'll learn a new way, a new force, and it's a force that couples the cell motility to the fields. Chemotaxis is very useful to model collective migration, to model emergent structures, and cell movement in general, signaling. Again, my name is Pedro dal Castel, and remember that this session is being recorded, live streamed, and distributed. We'll cover cell movements in gradients, and we'll model a simple version of chemotaxis. Movement in gradients is not only chemotaxis. Chemotaxis is only one type. There are also durotaxis, which is substrate rigidity. There is also aptotaxis, which is substrate adhesion, or molecules that are deposited in the substrate. Galvanotaxis or electrotaxis, which is when cells migrate towards or against gradients of electrical potential. There is thermotaxis, which is gradients of temperature. Phototaxis, light intensity. Rheotaxis, which is external fluid flow, guiding cell migration. And in this lecture, we are going to focus on chemotaxis, which is cell migration with respect to chemical solutions. So substances that are diluted in the medium. It's important in metastasis, cancer, in immune response. So defense cells will migrate towards gradients of, for example, cytokines. And angiogenesis to form the blood vessel structures, and we'll have an extra session on that. Wound healing, where cells follow gradients of dumps and also electrical gradients to close the wound, and also sperm guidance, which involves thermotaxis too. So chemotaxis is very well studied in a certain amoeba called Dictyostelium discoideum. In this cool video here, you pipette a droplet of a chemical substance called C-amp, cyclic amp, and the cells move towards the peak of concentration. In macro scale, they generate these spatial patterns, these complex spatial patterns, which is something you can simulate in CompuCell. In CompuCell, we model chemotaxis as a force that acts on the cell membrane, and this force is proportional to the gradient of the concentration. What is the gradient of the concentration? It's the spatial difference in concentration between two pixels. Multiplying that by the lambda chemotaxis will set the strength of this force. In a nutshell, what is going on here is that your membrane will copy pixels towards regions with higher chemical concentration. This very simple model can cause cells to move infinitely fast in steep gradients, and this can be an unintended effect, okay? In reality, when cells are in very, very steep gradients, they do not accelerate indefinitely. Their movement saturates somehow. Also, the cell movement will not cause advection of the signal. As cells move, they displace the molecules around them and then can cause feedback in the chemotaxis itself. And also, we are not considering that cells are removing the chemical from the environment. Any question here, or can I proceed? So far, so good? All right. So I built this diagram so you guys may better understand what's going on in terms of the algorithm. So here I imagined some field concentrations. So, and here I just care about the field concentrations in the border of the cell because that's where the chemotaxis is going to have an effect. So let's say that inside the cell border, in the inner pixels, I have these field values. And in the outside of the cell, I have these other field values. Now let's read this formula. This formula is saying that there will be an energy variation in our Potts algorithm whenever we make a copy of pixel towards a pixel target that has a higher chemical concentration than the source pixel. This difference multiplied by lambda chemical, the lambda, the chemotaxis lambda, is the energy variation. So let's say that the concentration in the target pixel, which is this term here, this left term, is higher than the concentration in the source pixel. So this number here is positive. And then multiplied by a lambda, by a certain parameter lambda, and then negative. Now this everything here is a negative number, which means our energy variation is negative. So in the Potts algorithm, this is a favorable copy. So with this formula, going up gradient is favorable. Is that clear? Avishak.
Yeah, so I'm a little bit confused. So you are only considering concentration on the border of the cell, right?
Yes.
So for example, a point that is in the middle of the cell that doesn't have any number associated with it might move towards kind of like a neighboring cell, right? With
A pixel that is inside the cell will not move. There is no such thing happening. A pixel inside the cell does not make copies with its neighbors because it's inside the cell. Copies in Potts only happen, all of them, it's not exclusive for chemotaxis, only happen in the border of the cell with some other cell.
Okay. And inside the cell, like the numbers represent the field concentration? Like, is it the concentration of what? Concentration
Field
of
concentration, any field imaginable.
Okay.
Katrin?
So in your picture, the numbers in the white fields indicate the concentration which is outside the cell, right?
Yes.
And why would then the concentration inside the cell be raising when the concentration outside the cell is increasing? This can only happen when we have diffusion, like water through aquaporins or something like that. But when we talk about cytokines, the concentration inside the cell is zero, so that the cell really can sense where to go. And when we look at this picture, the difference between 2 and 3 is 1. As as well as the difference between 1 and 2. So the cell here in this case does not know where is the highest concentration, right?
So there are many questions that inside your input. So I will try to address them one by one. So first, yes, it depends on the field, and sometimes it doesn't make sense for the field to be inside the cell. But we can imagine that this field that is inside the cell, quote unquote, is actually the substrate, is actually for example, underlying the cell or in the medium above it. So we can imagine this, and some other fields, for example, calcium field, will penetrate the cell, and
No, they won't. Why do you think so?
because of channels, calcium channels.
No, calcium sticks to proteins and will not get into the cell except you have a real attention difference. So voltage dependent calcium channels, for example, they will let calcium in, but usually you have the same concentration inside everywhere. It's the same.
Yeah, it does make sense. This will lead to a different I mean, here we are simplifying the system. We don't have advection. So
The biological application would be migration into the direction of, let's say, VEGF, for example, right? And
yes.
migration into the direction of calcium doesn't happen. So let's stick with VEGF, and VEGF is not going into the cell. So the question that I really have is, why do you implement a concentration gradient in the cell? Is this is this needed for the model, or is this somehow in the literature described like this, or why? What is the reason for this?
So the reason is this is a simple way of modeling, and the complex, the more truthful to biology way to model would be using advection of the signal, which we are not considering here.
So I repeat, maybe I was unclear. Now we have a concentration from 0 to 3, and the 2 is already the second highest concentration. But because in your cell model we have a boundary condition at the outer pixels, the outer red pixels, there are also 2, the cell will not sense this increase in concentration at the outside.
Yes, correct.
So why is this? Why did you put it like this? What is the meaning of this?
So the meaning here is that in this model, the cell is comparing the concentration inside it or underneath it, if this is a substrate, to the surrounding concentration, and a copy will happen in the direction of increasing gradient. So in this example, I am, in this exercise, let's say, I am putting random numbers, okay? They are random numbers. They came out of my head, my mind. And here, the cell is looking at where is the concentration increasing. So for example, 2 to 3 is increasing. So this would be where a copy would happen, and 2 to 2, it would not happen, and 2 to 1, it would not happen, 1 to 0, it would not happen. But the numbers themselves, they are generated. They are not trying to represent, for example, calcium signaling or VEGF. They are an arbitrary
I
field.
know, but we look at the difference, and the difference between 2 and 3 is 1, as well as the difference between 0 and 1 at the other side of the cell. So
Yeah.
there would not be a direction if we keep it like this.
I think it would. I think it would. So as the answer goes for this slide here, there would be preferential copies from 2 to 3 and 1 to 2, and no copies everywhere else. So there is a directional migration here happening.
Okay, and because it's let's say -1 at the other end, this is a retraction then. And we are
Yes.
not looking at the total difference at the
No.
but at the real with a sign plus or minus before.
Yes.
Okay.
But you are correct in your criticism of this model in terms of this is not exactly how a real signal happens in certain situations for certain fields. This could be more truthful to certain situations and not to other situations. But the overall effect that there is a gradient and the cell migrates towards that gradient, that's the final effect that we want to achieve. There are many ways to achieve that. This is the simplest of them.
Yeah, okay. Thank you. And sorry for
No problem.
all the
No, I think it's great that you people are engaging, and all these questions will come up eventually. So it's better that we can pause and discuss in the appropriate moment. Avishek.
Yeah, so we can discuss this later or right now. So I was wondering why certain cells like certain blocks inside of the cell do not have any numbers assigned to them.
Oh yeah,
Okay.
so this correlates with your previous question. So I don't care about the concentration values inside the cell because those pixels will not make copies anyways.
Okay.
So the chemotaxis only acts in the border of the cell. So if there is 100 here, it's not going to change the answer. And if
Okay.
there is 100 over here, it's also not going to change the answer unless the border, the interface between medium and cell comes in contact with that gradient difference, that field difference.
Got it. Thank you.
No problem. Okay, so I think we covered more or less how this works. So you have a gradient and pixel copies will be made in the direction of the gradient. And you can also set a negative lambda chemotaxis. If you set a negative lambda chemotaxis, then these arrows would be inverted and the cell would preferentially migrate towards this 1 to 0 direction here. So some cells migrate up gradient of something and other cells can migrate down gradient of something. In CompuCell, this very simple chemotaxis plugin has different settings that you can specify. For example, what is the chemical field responsible for generating the chemotaxis? So in your chemotaxis plugin, you will put the name of the field. Is it, let's say you have the oxygen and the waste field. You can type oxygen and you can type waste. And if you want both to do something, you should duplicate this block and say one is for oxygen, the other is for waste. Now you have type cell type. So in this last option here, what is the cell type that obeys the chemotaxis? So in this piece of code, cell A is obeying the chemotaxis with respect to the field. We also set the lambda. So this number here, 500, this is the lambda chemotaxis. It is the intensity of chemotaxis. How much force is the membrane experiencing for a given gradient? So this gradient, this field difference is multiplied by lambda, which then converts to works as an energy difference. And finally, there is this important final option, chemotax towards. And chemotax towards tells the cell that it can only perform chemotaxis when in contact with a certain cell. So if you say cell A chemotax towards cell B, these two pixels here, xt and xs, they have to belong respectively to cell A and cell B, or the other way around. This one cell B and this one cell A. They have to belong to either cell A or cell B so that chemotaxis work. Jupiter, I will open a paint here and try to explain how this is working. So I have cell A here, and I have cell B here. And then I have cell C here, okay? But my chemotaxis is towards cell B. Okay, my chemotaxis is towards cell B. And let's say I have a gradient in the upwards direction. All right, I have a gradient in the upwards direction. And my chemotaxis is towards cell B. So the pixel copies will happen here only. And they will not happen here. Here, it's going to be neutral. Is that clear?
Unfortunately not, at least not to me. The arrow points towards the higher concentration, right?
Yes.
So B is the cell which undergoes chemotaxis.
No, A is the cell that undergoes chemotaxis. I'm sorry for that. So cell A undergoes chemotaxis towards cell B.
Which is not possible because cell B is already there and doesn't move.
It is possible. What is going to happen is that pixels from cell A will replace pixels from cell B.
And what happens to cell B? Is it eaten?
Cell B is going to be pushed.
Does this happen in nature, Pedro?
I don't know. It might happen, and then we have to simulate it somehow. But generally, what we do is actually use the chemotaxis towards to inhibit chemotaxis towards cells by doing chemotaxis towards medium. So if I say to cell A, you only chemotax towards medium, then this doesn't happen, and the cell A will not move past cell B and C, only if cell B and C are medium. If they are medium, then cell A will move. So that's how we use the chemotax towards option. And James is saying yes, they do.
Yeah, usually they don't, because when you have a gradient like this, the cell A will move either between B and C or make a hole in cell B or in cell C and move that way. But that there is a real movement which pushes cells which are in the way, I don't know.
Yeah, I don't know either. What do I know about biology? Nothing. Okay.
Yeah.
So I can't I'm not a good, maybe you can discuss with James in chat. I think that's a good discussion. But I lack the knowledge, sincerely. This is a very complicated interaction we're talking about. So I'll have to move on, but I appreciate the discussion. The Chemotaxis plugin also allows other options, such as saturated chemotaxis, which inhibits chemotaxis for very large concentrations. For that, I will leave you guys with the documentation. So I will remind you guys of code snippets. This will be important in our lecture. So to access code snippets specifically for this lecture, in CC3D ML menu, plugins, you can find the Chemotaxis plugin if you lack your Chemotaxis plugin in the XML. And if you are in Python, CC3D Python scientific plots setup, you can set your scientific plots, okay? So we will use plots in this lecture, and you can grab these code snippets prepared for you that you have to edit by accessing the code snippets. So we have an exercise now of chemotaxis, and take your time to do it. I will give you 3 minutes to reach step 4. And I love Sharon input here. It's just a tool. The modeler decides how they want the cells to behave, and it's not an assertion of what's real. I think I have to save this. I have to save this and put this somewhere because this is so valuable. I will send an email to myself with this. Sharon teaching about modeling. Thank you, Sharon. So please, guys, go ahead and do the exercise. Reach step 4. Once you reach step 4, I will guide you guys through the chemotaxis wizard.
And just to confirm, we're not supposed to move from the Chemotaxis plugin page. We're just supposed to wait there.
Yeah, yours. Yes, wait there.
Cool. Thank you.
No problem. So let me see how you guys are doing with this. You can also grab the simulation ready to go from the drive, the Google Drive. You can download the entire folder for session 4.2 and run the individual simulations.
I'm sorry, where is the uniform initializer?
The uniform initializer is the rectangular slab option.
Okay, thank you.
This one. This will give you the uniform initializer.
So we don't need to plug in anything in the cell properties and behaviors window.
You do. So point 3, number 3 in behaviors, enable contact, volume flags, and chemotaxis.
And how about the center mass and cell neighbors? So we keep them tickled.
Yes, keep them.
Okay.
Yeah.
Great, thank you.
Okay, so I will proceed. Now we are seeing this Chemotaxis plugin window, and you want to specify a lambda chemotaxis 500, enable chemotaxis towards medium, and chemotaxis type regular, and then you hit add entry. That's what you want to do. And notice that you here in this page, if you had many field types and many cell types, you would click these two drop-down menus to select which ones, which field interacts with which cell.
Pedro,
Mhm.
I don't understand that line that says cell type medium toward medium.
Yeah. So to enable chemotaxis, chemotax towards medium, you can simply type medium in the field 2. And
But
Drop down for
sorry?
what is the drop down?
The
Next to
drop down is so that you don't need to type you don't need to, if you don't remember your cell types, the drop down selects a cell type for you, and then you click the chemotax towards button and it writes in the field for you.
Okay, I don't understand, but go on.
Yes. Yeah, so to enable the chemotaxis towards medium, just type medium in that blank field and hit add entry. And then you know your settings are correct when you see in the table, in the Chemotaxis plugin table, the field name, the cell type, the lambda, the chemotax towards medium, and regular type with no set coef, no saturation coefficient. Ali, saturation coefficient is not in this lecture. I will talk about it later. Okay, so setting that correctly, you should be able to hit next. Can I go over the process? Of course. So please, everybody that is doubtful about this exercise, stop and look at the streaming, okay? Because I will go over the process now. So I have my chemotaxis table here. I first 500 in lambda. That's the first step. So what I did, 500 in the lambda field right here. Next, chemotaxis towards medium. So in this blank field, I will type medium with uppercase M, the first M, okay? I will do this again. In the chemotaxis towards blank field, I will type medium with uppercase M. This is the second step. Third step is choosing regular. So in this step, we don't need to do anything because by default, it selects regular for us. And then add entry. So here I see my field oxygen, my cell type cell, my lambda 500, chemotax towards medium, and type regular. Okay, we are good. I'll proceed. Next step is you hit finish, you have your simulation, and you guys are tired of going through steps, so you'll do this exercise alone. And in this exercise, you have to create a linear gradient and initialize a single cell in the right-hand side of the X domain. There are tips about how to create a linear gradient from your XML, and how to make it linear from the beginning of the simulation too. So I will give you guys 5 minutes to follow these steps. How much time we have left, Hayden? 30 minutes or what?
We go until 1:15.
1:15. Okay, so I have 45 minutes. Okay, that's enough. I will be able to cover the linear field, the exponential field, and then I will choose between the self-generated gradient and the exploring parameters. Yes, it is a regular type, Liam. Yes, this is regular type. Yes. It doesn't say regular anywhere, but yes, it is regular. In the documentation, you can see how to implement the non-regular types. So someone asked about what is saturation coefficient. I will direct you to the documentation. It's in the slide somewhere. Where is it? Here. This is the documentation. It explores all aspects of chemotaxis. So feel free to read that through and learn how the saturation work. But not now, okay? Please pay attention to the lecture. Otherwise, later, oh, I can't do the exercise because I was reading the saturation.
I have
Where
a
to find
question.
initial condition. The initial condition is your initializer, your blob initializer or uniform initializer in the XML, Kimberly. Avishek?
Yeah, I had a question. So you mentioned set X boundary to constant value from 1 to 0. So does it mean that in the boundary conditions that constant value of x, the minimum should be 1? Minimum should be 0, right?
Minimum should be 0, yes, 1 to 0.
Oh.
So in your x min, in your constant value x min 0, and constant value x max was
Okay.
0.
Okay.
Sorry, I think I messed it up. In your constant value boundary condition x minimum, you put that to 1 and the max to 0.
Okay.
All right. And then your y boundary conditions are periodic. Where to
So,
find?
so the template for constant value doesn't even have a max. We add a line for that.
Can you repeat that? Sorry, my brain shut down a bit.
The template that's provided with the XML gives a min and max for constant derivative, but not for constant value. It just has min. Do we add another line to give it a max?
Wow. Does it do that? Let me
And
see.
what do you mean by a max that's smaller than the min?
X max is the right border and min is the left border. Uh-huh. Or let me take this one. Open the XML. How is this looking? So here we have constant value in the minimum plane position 1. That's okay. And constant value 0 in the max. That's okay.
Okay, so that line isn't in mine. I have to add that. That's okay. I'm adding it.
Okay.
I can't say I understand the meaning of the numbers.
Yeah. Min is the left or bottom. Max is the right or top. Yeah. It's not in yours too? Huh. So, yes, because, okay. So you can also download this demo if you want, but yes, you have to set your boundary conditions. It is commented. The appropriate boundary condition is commented in your code somewhere.
But this steppable type is blob, not uniform.
That's okay. It doesn't change the simulation.
I still don't understand the initial condition under the uniform initializer. I don't see an option for that.
Okay, so let me open my XML and show you. So here the uniform initializer, which is my case. What is yours?
Uniform.
Okay, so here you create your cell. So this is the box min and box max is a square, and you set the minimum vertex of the box and the maximum vertex of the box in X and Y coordinates. So if you do, for example, 50 to 60 and 50 to 60 in both, and then set a width to 10, effectively what you are doing is creating one cell in the middle of your box, in the middle of your lattice, more or less.
Yeah. Okay.
All right.
I also have a question. I made what we were supposed to do, and now I try to open it in Player, and it doesn't open in Player. How can this happen?
Can someone go to a breakout room with Catherine? Because player crashes, we might take a while to solve.
I have one question. How do we set the initial condition that should be 1 minus x divided by 200?
Okay,
What
so
does it
you
mean?
set the initial condition in your fields in the XML. There is this line called initial concentration expression. You uncomment this line and set the 1 minus x over 200. Is that clear?
Need a little bit time. Let me find the line. It's
Omar got it. Okay. Is your cell chemotacting, Omar? Good. So, Huixa, you may look at what I'm doing here. So tell me when you are looking, because I want to go fast here.
okay.
So uncomment, control bar, 1 minus x over 200. That's your initial condition.
Okay.
All right? Okay. Let me get back to my slides. I will launch the poll to see how you guys are doing with the exercise.
Ugh.
Okay, you need more time. I will give you 5 more minutes. So Liam, check your XML. So let me see with 10. That looks that. Oh yeah, so it's incorrect. Because your y coordinate doesn't go to 160. Your y coordinate just goes to 100. So that is not correct, Liam. So if lambda is higher, will the cell move faster? Good question from Yasmina. Yes. Yes. Yes, Mohit, that's correct. That's correct. You should adjust the mean and maximum if you fix them to match the mean and the minimum and maximum of your field. Huik said, no, this is not correct. You should be creating one cell in the right-hand side.
Okay.
Yes, okay, good, got it.
Yeah. Yes, Erin is absolutely correct and accurate. Your cell still doesn't appear, so try this. Try this. And also show me how is your Potts initialization, this section right here. Show me how this is. I will launch the poll again. Let's see how you guys are doing. Yeah, that's correct. Huix, your field is weird though. Something not quite right there. Yeah, it looks okay. Your field is inverted, Sheriff. Your field is inverted. It does make sense, but it's inverted. You should invert your field grade, your gradient. Avishak, that's correct. The field shouldn't change over time because you're initializing it in the steady state already. 200, 200. Okay. Oh, interesting. So yes, Liam, I don't know why yours is not working. You might want to join a breakout room with someone. Do we have TAs present? Yes, we have many. We have Lorenzo. and Hayden. All right. Okay. Yeah, Huix, your field is the other way around. Yeah, Hayden is not available. Maybe Lorenzo can help you guys when in a TA room. Huix,
Okay.
yes, your field is the other way around, so yes, it will change over time.
Okay. I will go to a break. Thank you.
Okay, I will proceed this. Please, if you were not able to follow through, download the simulation from Drive. So I will send you guys the link, and go ahead and download the module 4.2 demos. And in the module 4.2 demos, you'll find the linear chemotaxis demonstration. All right. Let me see. All right, so now we're going to build a plot. So use the code snippets to build a plot, and what you want to do is plot the X position of the cell in respect to time. So in start function, you should have these settings, the acquisition of the plot window object, and then the addition of a plot to that plot window. And then in the step function, you add a data point where the x-axis is the MCS, the time step, and the y-axis is the cell center of mass, X position. So do that, and remember that you can use to edit code snippets. If you're not able to follow until here, download the simulation and then you're done. I'll give you 5 minutes on this one. Linear, so no, the one you open into edit is the .cc3D file. It's on the upper file from this one. Wait. So it's this one, linear gradient chemotaxis.cc3D. This is the one you want to open. And again, this is wrong. This is not a linear gradient. I hate this. It's linear field. The gradient is constant. Incorrect. So this is downloads module 4.2 demos, and then linear gradient, chemotaxis, linear gradient. This is the one. Avishek got it right. That's correct. So your cell goes to negative X position and then hits the wall and
Can you
stops.
please leave that slide there so we can see it? I can't get finished.
Yeah, sure. So when I do this, can you see the slide when I do this?
No, you're covering it.
Oh, okay. So when I'm using the chat, somehow the slides get covered. That's interesting. I didn't know about that. Okay. Yeah, Zoom is not smart enough yet. So good. I see that people are getting the plots working. That's fantastic. Good progress. And this I will put to the side, exactly what you guys got. Those tile. It should tile vertically.
Just a basic question. Every time we call back the excon attribute of a cell, that's the center of the cell always, right?
Yeah, center
Like
of
the
mass.
X position, center of mass. Perfect.
Yes. I don't know what else it could be, but yes, it's the center of
I was
mass.
thinking it could have been like the, I don't know, some of the boundaries or some of the edges, but just to confirm, center of mass. Oh, COM, of course.
Yes,
Okay,
COM.
that makes sense now. Thank you.
All right. I will launch the poll again, see how you guys are doing. How are you doing, Sharon, with the exercise?
Got it. Thank you.
Nice, good. Okay. I think we got a good completion sample, so I'll move forward. Now we're going to talk about adaptation of the lambda chemotaxis. So when in general, the field profiles is exponential because some cell is secreting something and that something is decaying somewhere. So the resulting signal of the field when it reaches the chemotaxing cell is an exponential profile of a field. So our cell with the regular chemotaxis is not going to respond very well to the exponential field. In the lower part of the exponential field, it's going to chemotax very slowly. And then in the very steep gradient of the exponential field, it can even destroy the cell because it's too steep. And this is also biologically realistic because cells might have amplification and saturation mechanisms to the signal to the signal being transduced. So to implement the adaptation of lambda chemotaxis, we need to understand how to manage chemotaxis from Python. This is completely possible in Python. You can interactively edit the XML by accessing the plugin data. So for example, you can set individually, cell by cell, a specific lambda chemotaxis. So if you get the object add chemotaxis data for a specific cell and a specific field, you can set a specific lambda chemotaxis. So you can have many cells of a single type with different lambda chemotaxis. What we are going to need for this next exercise is not setting a specific, is not the first one, is not adding chemotaxis data. We already have chemotaxis data. We want to get chemotaxis data and update it. And we'll do this by using the command self.chemotaxis plugin .get chemotaxis data for a specific cell, specific field, and then generate a new lambda by getting from this object using the get lambda function, getting the lambda chemotaxis value. Then in this silly example, it is taking that lambda value and decreasing it by 3, and then updating the lambda value by using the command cd.set lambda, and then the new lambda parameter. Who has a question here? Is this clear? Okay, I will proceed. So for this next exercise, what you want to do is update your lambda chemotaxis by dividing it by the concentration. So when you divide it by the concentration, it's as if the cell is calibrating its lambda chemotaxis based on the level of chemical in the field. So if the level is very low, the response will be very high because it's trying to balance the lack of signal. And if the concentration is very, very high, it's going to lower the response to the signal because the signal is very, very steep. So in this exercise, what you want to do is build an exponential gradient. And the exponential gradient, you build it by setting a global decay coefficient to your simulation of 0.0001, for example. And then you take advantage of this exponential gradient profile and already set the initial condition to be the same as the concentration at equilibrium, which is given by the exponential function. And it is given by e to the minus square root of gamma over d. Gamma is the decay, d is the diffusion constant, times x. So the initial condition should be this expression here. You can copy and paste this into your initial concentration expression. So let me help you guys and copy and paste it in the chat, this expression, to help you building this one. This expression goes to the initial concentration expression. Yes, thank you, Iran. Try, as I think it's 1, yeah, 1 to the 3 doesn't, 1 to the 30 is, it seems a bit too much. I think that's correct. Yeah. 10 to the 30s doesn't seem you know, what is S? S is a parameter that you add to the concentration to prevent a division by 0. Oof. Because if your concentration is 0, Iran, so what value you put for S? Any? You can put like 0.00000001. It's just a parameter that you use to prevent a division by 0 in your code. Do we need to add manually the lambda chemo? I can't find. Yes, you need to add by using these commands here. I will copy and paste them in the chat. So you use these commands to update your lambda chemotaxis value. So where do you update a parameter that is specific to a certain cell? In your step function, inside of a cell loop. In the for cell, in self-cell list, inside the cell loop, you take the lambda chemotaxis parameter and update it. Right? Because you want that to be updated every time. So it has to be inside the step function and it has to apply to all cells in your simulation. So inside the loop over cells, right? Does that make sense? You get the here and use the to edit code snippets. So CC3D Python, chemical field manipulation, get field, and then yeah, that's how you do it. Using the to edit code snippets. The initializing code is also in step function. Yeah, no. The initializing code has to. What is the initializing code? Yeah, Zirin, but then you edit this to be filled at the cell.xcom, cell.ycom, and 0 using the cell center of mass. Yes, you also need to get the object field. So go to the to edit code snippets, chemical field manipulation, get manipulation, and get field reference. Yes, Ali, yes. You have, yes, exactly. You have to set to lambda over S plus concentration. Yiran, yes, you write the name of your field in place of field name, and it has to match the exactly how you wrote your field name in XML. It has to match exactly. All upper or lowercase letters have to match. Okay. So I see that some people got it right. If you were not able to follow, you can open the simulation from the Google Drive. Get the simulation from Google Drive. Okay. Let's see how we are in terms of the exercise. How is exercise completion here? So, and this is important. From now on, guys, we will not go step by step with you. We will give you the instructions and you have to build your own simulation, because the purpose of this workshop is making you an independent modeler able to build a simulation in CompuCell. So this struggle of, oh, where do I find this? Where do I find that? How do I read the documentation? This is part of the process, okay? I see that one person needs help. Please ask for help in chat, and Yiren, check if your oxygen, if the name matches exactly the name in XML. How do you get CCOM? No, Ali. you get the field concentration at the cell center of mass. Let me give you the look. Oh, everybody stop and look at me. Everybody stop and look at the streaming. Okay, everybody. I am in the step function. What am I going to do to get the field concentration at the cell center of mass? CC3D Python. Okay, chemical field manipulation. First, get field reference. We need a field object. So now I have the field reference. This field name has to be exactly the name of the field in XML. So I go to my XML, I see that the name of the field is field. So I come back here and I type field. Looks silly, field equals self-field.field, but that's how it is. Now, don't move, don't open your simulation. Keep looking at the stream. CC3D Python, chemical field manipulation, and now get field value. And now I receive this. So value is field and then a certain coordinate. So what I am going to do here is change this coordinate by the cell position. Put here the cell position. So cell.xcom for x center of mass. Here it's going to be cell.y center of mass, and this is 0. So this is what you guys want. All right, so now for real, if you were not able to follow, download the simulation and get the simulation ready. What you should be able to see here is that without division by the concentration, you see this unnatural curve where not unnatural, but the cell is super slow in the beginning and it suddenly goes extremely fast, indefinitely fast. While when you regulate by the concentration value, the cell smoothly crosses the exponential field with roughly the same speed. Okay, so this will be a homework for you, which is you multiply your lambda chemotaxis by a factor of minus 1.2 every 1,000 Monte Carlo steps. So your cell will be like migrating left and right, left and right, left and right, and at faster paces. And what you should see with this is that in a certain regime, for lower lambda parameters, your cell gets faster and faster, but it reaches a limit. After a certain lambda parameter, if you keep increasing it, your cell will not increase its speed because there is a limit speed in CompuCell. Cells can only copy 1 pixel per Monte Carlo step, so there is an inherent speed limit. This will be a homework for you. Please do it if you intend to implement chemotaxis in your simulations. And the final example here, which unfortunately will also be a homework, but I will show you guys the simulation running. So please stick with me. I will talk a little bit about the mechanisms behind the simulation and maybe the biological meaning, and then Catherine will teach me some biology. And the actual building of this model will be left as a homework. Okay, so this exercise is the chemotaxis in response to self-generated gradient. What is a self-generated gradient? Our cell is sitting in a field and it consumes the field. As it consumes the field gets depleted and it generates a gradient. All right? When it generates a gradient, our cell, because it has chemotaxis capability, it will follow the gradient. So our amoeba here is consuming nutrient, which is in the medium. And as it displaces, it leaves a nutrient deficit trail behind it. And because it's always moving up gradient, it tends to avoid the path that it once was, that it once crossed. So it's a cell that avoids its previous positions. And we can create with that random persistent movement. So our dynamics is medium starts with a pre-existing field, a nutrient field, a substrate, and our cell consumes the chemical locally. And then because of small fluctuations in the membrane, the cell displaces a bit and identifies a gradient in this field, because the field gets depleted locally and it's higher in the vicinity of the cell. And then finally, the cell chemotaxed towards higher chemical concentrations, and it avoids its own trail. So it will migrate persistently. So this is exercise. This is the exercise. This will be left as a homework. I will describe here what you have to do. So you have to create a small square lattice of 100 by 100, create one type of cell, an amoeba, and a field nutrient. You will choose contact, chemotaxis, and volume constraints. Then in the XML, you set the global diffusion and decay coefficients to 0. And a specific cell decay coefficient of 0.01, which means our cell is absorbing this nutrient field. Set the field boundary conditions to periodic, as well as the cell lattice boundary conditions to periodic, and initial concentration of the field to be 1 everywhere. Then set the chemotaxis lambda to 200 and initialize a single cell in the center of the simulation. And then you run the simulation. The simulation is ready to go, and I will open and run. Where is it? On self-constructed gradient. So now here, discard this, close this. Open this in player. Yes. So we can see here, I will get another window by clicking in new graphics window button, and then I will go and hit tile. So it organizes the windows for me. And here we can see what's going on. You can exactly see how cells are avoiding. Look, this is super interesting. Look at this. Look at what the cells are doing. They are trying to avoid both left and right trails because they are nutrient depleted trails. So they are avoiding it and they are trying to cross exactly in the middle of the two paths. And the other cell over there is migrating freely, persistently, with some random fluctuations. And as they leave this trail behind, they have this self-avoidance interaction. As you can see here again, what happened over there, the cell entered in contact with another nutrient depleted region and then changed its path to a higher concentration region.
This is kind of a devil's advocate question. If would the program get stuck if something were kind of stuck on an island of nutrients, but surrounding it was a deficit of nutrients? Could the cell be smart enough to know that it could cross over a moat of no nutrients to get to a field of high, of nutrients?
Good question. So no, and this is comes down to the concept of locality. The cell only has, information from the location it is right now, unless somehow information is being transmitted from long distances, which is super, super uncommon in biology. So if you assume, it's a very reasonable assumption that our simulation, our model is a local model, then that cell stuck in a nutrient depleted, was surrounded with a nutrient depleted region, will not be able to cross it.
Except
One
that
way,
I've
one way
watched
to
that happen.
Go ahead, Sharon, sorry.
Sorry, I've watched that happen a couple times while you were discussing it. It does
Yeah.
cross. It may not be knowing that it needs to, but once everything's depleted, it just goes randomly and finds its way
Yeah.
out.
Sure, yes. So there are 2 points here. First, when they get stuck here, for example, this one, it gets stuck for a moment, but soon the nutrient inside the cell will be lower than the nutrients surrounding it. So even though this might look at this, this might look at a low nutrient, you will see that this becomes very, very blue very quickly, and then the surroundings are higher concentration. But if we assume a situation like the one Kimberly described, where the cell is like surrounded by zero, absolute zero nutrient, the only thing that might make the cell cross these potential boundary is random movement, for example. So if we introduce a random movement, an inherent persistent motion to these cells, it might probabilistically reach another region with nutrients available. So I think this is officially Q&A. I would like people to ask questions if you have any. In the meanwhile, I will launch the module questionnaire poll. So let me go ahead, stop this. And as a homework, please build the self-generated gradient. This is a very cool simulation. And this is one of the few very, very, very simple simulations in CompuCell that is very much meaningful in terms of biology. So please take a minute to fill out the poll. I will launch the module questionnaire. And we are officially open for Q&A. Good question from the chat. When you're set in Python, the Python setting should overwrite the XML setting.